with us this afternoon Professor Takao Someya from the University of Tokyo. And of course, I hope many of you have taken the brochure coming in, but one of the striking features in the case of Professor Someya is not only his excellence in research and pushing research into technology, and you will have many examples of that for us, but also, and especially in a country where things have not always been set in terms of pushing multidisciplinary research. He is certainly one of the pioneers in that case, and that's the reason why I actually got the first chair established in terms of multidisciplinary research at the University of Tokyo back in 2009. He's also very much involved in the professional societies, and for instance, he's a member of the board of directors of the Materials Research Society. And of course, well, of course, for those of you who know his work, it comes as no surprise that he has been awarded quite a number of prestigious awards. Among them, the German Innovation Award, the first of its kind, and also a prize from the Japan Society for the Promotion of Science. And interestingly, that's a prize that is being awarded in the presence of the Crown Prince, which must be one of the very few opportunities to meet the imperial family, I'm sure. But without further ado, I'd like to leave the floor to Professor Someya, and join me already in thanking him for spending his time with us today.
Thank you very much, Professor Braille, for your kind introduction, and good afternoon. I feel really honored and quite excited to share with you our recent progress of stretchable and flexible electronic stuff. So my name is Takao Someya from University of Tokyo. Today, I'd like to convince you why I believe the flexible electronics is so important, and how flexible electronics is going to change the future of your life as well as the future of electronics. So I always try to show some of our latest prototype of flexible devices. So for example, some groups start showing the bendable TFTs. However, we can do better job. I mean, this is the organic transistor integrated circuit manufactured on 13 micron plastic film, which is functional even when that's wrapped around the cylindrical bar in 1 millimeter diameter. And also we have made the foldable TFTs. So this picture does not show you the surface of plastic film, but if you look at the edge, here is also integrated circuit, which is functional without causing any degradation even when we squeeze the transistor film completely. Another example is stretchable TFT active matrix. So we spent a lot of time to build the integrated circuit on rubber substrate to make the integrated circuit stretchable. And the last picture is crumpled material. So this is not integrated circuit, just a material, but we we electrically functionalized the surface of cellulose by using single-walled carbon nanochip to make the paper highly conductive. So we believe this is the quite important material to make the crumpled electronics. So those pictures gave you some of the rough images of our activities in Tokyo. So this is the outline of my talk. After a brief introduction, I will first describe the printing processes like inkjet and screen printing, and then I go on talk about the flexible thin film transistor technologies using organic semiconductors. And then I will describe the robotic skin and some of the other applications. And finally, I will summarize my talk. So, in 2003, our group proposed the robotic E-skin as one of the possible applications of flexible organic thin film transistors. And then we manufactured the robotic skin to demonstrate the feasibility of organic thin film transistors. As many of you know, the robot or machines has already get the quite nice artificial vision, which means CCD camera, or artificial ears. That means microphone or acoustic devices. However, there has been no practical flexible devices that allows the robot to obtain the touch sensitivity over large area. So 3 years later, we have made the second generation of robotic skins. So that allowed us to get the multiple touch sensing and pressure distribution, real-time sensing, and somehow grayscale is available. So, but surprising thing is that we have made these devices in 2006 and kept in ambient condition for 6 years. However, this device is still functional, so without causing any significant degradation. So some of you may concern about the degradation or reliability, stability issues of organic electronics. However, the E-skin just use the P-type organic semiconductors, and then we have less concern about the reliability issues because some of the organic semiconductor, P-type semiconductors, is extremely stable in air. And then suddenly touch panel appears and creating the iPhone or iPad or other modern communication devices. And then people recognize how important the touch sensitivity is. In fact, the small kids and senior people can easily change the font of size just doing like that, so without reading the thick book or thick manual. So in this way, people now recognize the how, well, touch sensitivity is quite intuitive and to make machines more human friendly. So the latest effort to make the machines more human friendly is quite new research trend. But before that, many engineers or researchers in the field of electronics is trying to make the machines faster with improving the calculation speed faster or improving the memory storage capacity larger. So that can be done quite easily by using the silicon-based mainstream electronics. So just miniaturizing the device dimensions. So in 2003, which is exactly when we developed the first generation of robotic skin, so one of the big electronic company in Japan has successfully fabricated the 4 nanometer thick, 4 nanometer channel length transistors. So now the transistor community is approaching its fundamental limitations, which is of course the major concern in the field of electronics. However, of course, the making machine is extremely important. Machine faster is important, but now we try to compete with the making machine more human friendly. And then some of the new devices will play a very important role in the future. So here I would like to introduce the organic transistor. What is the organic transistor? That is a soft electronic switch using organic semiconductor as channel layer. So this device has extremely interesting and attractive features that is complementary to the mainstream silicon. So organic semiconductor can be nicely deposited on plastic film at ambient temperature by printing or other solution process. So people can make the organic transistor, flexible organic transistor, quite easily with reasonable price. However, well, when we started the research of organic transistor, so many people claim or recognize organic transistor is a kind of cheap devices. But here we should be a little bit careful because there are two different types of cost to argue. So one is the cost per function, which play a very important role to discuss about processor and memories. So again, silicon is good at miniaturizing its device size. And then, if we try to consider the cost per functions, silicon is always win. So what is the good aspect of organic transistors? So here is the another consideration for cost. That is the cost per area. So as again, the organic transistor can be printed or can be manufactured by other solution process. And then we can significantly reduce the cost per area, which should play a very important role, sensors, actuators, displays, and even more. So then we noticed the organic transistor is really strong when we try to apply for a large area. And then we start looking for some of the new applications that really required large area. So in this slide, I try to describe the technology trend in large area electronics. So in the field of large area electronics, solar cells and displays have already established a huge market. So it started the bulky devices like CRT going to thin, lightweight, and now the display becomes bendable and rollable. So those new research fields is often referred to as flexible electronics and attract the much attention. So one of the great benefits to manufacture the electronics on plastic is mechanical durability. And we borrowed this movie from Samsung Mobile Display, and they really made the unbreakable OLED displays, so which manufactured on plastic film. So it's extraordinarily mechanically durable. And of course, displays is very important industry. However, we are looking for some of the other new applications, that is large area sensors and large area actuators. So E-skin is quite a good example as one of the large area sensor application. So in order to apply E-skins onto a joint of robotics arm, so that have to be stretchable. And also in order to apply the robotic skin onto a three-dimensionally curved surface, so that have to be conformable. So in that way, large area electronics have to be further advanced to be conformable and elastic. So and then those new research fields is often referred to as stretchable electronics and attract the much attention quite recently. So however, here is the chicken and egg problem. So mechanical robustness is usually limited by fragile component. However, electronic performance of soft material is usually quite poor, and then people inclined to use the rigid component, but that is not mechanically flexible. So mechanical durability and high electronic performance is always trade-off. So we cannot compromise everything together. So how we can solve this problem? So thanks to recent progress of material science, so then if we use the graphene carbon nanotube, such kind of nanocarbon or organic material, organic molecules, so if I use such kind of novel nanomaterials, so there is some hope to solve this kind of problem. So then I would like to start talking about the printing process. So in order to make the large area prototype, so printing processes play very important role. So this movie shows you the direct writing of silver electrode using the silver nanoparticles. So here, the silver nanoparticle comprises the 2 or 3 nanometer dot, and that will be delivered onto a surface of plastic film. And after the direct writing of silver electrode on plastic film, the substrate was annealed at 160 degrees Celsius or so to get the dense silver film. So in order to apply the printing processes for the active device application, and then one of the major concerns is spatial resolution. So, and then here is a new development. The typical conventional inkjet can control the tiny droplet with accuracy of 1 picoliter. But now we apply the external field between tip of nozzle, inkjet nozzle, and substrate. And now we can control the droplet precisely in the sub-femtoliter accuracy, which corresponds to 1.5 micron in diameter. So by using the novel sub-femtoliter inkjet, now we can write the extraordinary fine pattern, something like that, in a resolution of 1 or 2 micron on any kinds of substrate. So in order to improve the device performance, of course, this is active component. So naive control of interfacial quality is extraordinarily important. So this is one of the good examples. So if I use the, if I deposit the gold by evaporation on the surface of semiconductors, so now here you can see the abrupt interfaces can be nicely formed. However, if I use the picoliter inkjet, here is a problem. So organic solvent is penetrating into a semiconductor region. So now you cannot see any interface. However, if I use the sub-femtoliter inkjet, all the organic solvent is vaporized before that reach to the substrate. And then we can avoid the organic solvent associated degradation. So in this way, we can fairly nicely control the interfacial quality. And inkjet maybe the throughput of inkjet may not be so good. So if throughput is your primary concern, so I want to suggest you to use the screen printing. So as you look at this movie, the fine pattern with resolution of 20 micron can be done in a few seconds. So in order to improve the spatial resolution of screen printing, we have to optimize the 3 kinds of things. One is the screen mask and viscosity of optimization of viscosity of ink. And also, we have to play around the process printing parameters. But anyway, if I use the 12-wave stainless steel mask to improve the tensile force. So now we can apply really high viscosity ink, something like 360 pascal a second. So with combining the high tensile strain mask and also high viscosity ink, so we can reproducibly print the 18 micron fine patterns by screen printing. So as perhaps you know, screen printing has been already used in mass production plasma display factory. So our group has the screen printing machine in our clean room, and combining inkjet and screen printing. So we can make the organic transistor active matrix on 40 by 40 square centimeters plastic film. So then I would like to talk about the flexible thin film transistors. So in order to make the large-scale sensor matrix, the active matrix play a very important role. So there are so many different materials competing each other. So one is polysilicon, obviously, and also metal oxide appeared recently, and another important choice is amorphous silicon, and we are working on organic transistors. So although those different approaches are competing each other, if you look at this table, like mobility as one of the important performance index as electronic properties, and voltage bending radius as a part of the other representing properties of mechanical durability. So it is extraordinarily difficult to achieve the high mobility, low operation voltage, and sharp bending radius simultaneously. So in order to achieve everything together at once, so here is our preferred device structure. So we use the self-assembled monolayer as gate dielectric layer. So here is the cross-sectional TM image and corresponding device structures. So here is substrate, and aluminum gate is deposited by vacuum evaporation, and surface of aluminum layer is intentionally oxidized by plasma to form the 4 nanometer thick aluminum oxide. And then this substrate is dipped into an organic solvent having octadecyl phosphonic acid to form the 2 nanometer thick self-assembled monolayer. Then we deposit the pentacene or other semiconductor layer and print or deposit the gold as source drain electrode. So in this TM cross-sectional view, you can clearly observe the abrupt interfaces can be nicely formed. So of course, the formation of self-assembled monolayer is well-known phenomena, and all the chemists knows the self-assembled monolayer. However, one of the most important contribution from our group is something like that. So the some layer is nicely formed on quite flat surface like glass, silicon oxide, or some of the other smooth surface with nice monolayer atomically flat substrate. However, if we try to make the same self-assembled monolayer on plastic, so here is a problem. As you can see, the surface of plastic film is quite rough, so we cannot form nice self-assembled monolayer without causing the pinholes. So to avoid that problem, so here we deposit the quite good surface planarization layer using polyimide precursors, and then we achieve the almost equivalent surface smoothness. So in such a smooth surface, we can nicely form the self-assembled monolayer. So this was one of the most important contributions in our group. So in this way, we can reproduce the the fabrication of high mobility organic transistors on plastic film or any other substrate. So thanks to a thin film feature of self-assembled monolayer, So operation voltage was as low as 2 volt, yet we can achieve the high mobility on plastic film. So if I use the pentacene, that is typically from 0.5 to 1 square centimeters per volt second. And if I use the high mobility semiconductors, that can be improved significantly. So now I'd like to show you the bending experiment. So if I make the organic transistors on 75 micron plastic film, the minimum bending radius was 4 millimeter. However, we can do a better job if I manufactured similar organic transistors on 13 micron plastic film, and then that is covered by a 13 micron thick encapsulation layer. So in this way, the organic transistor can be set to be a neutral strain position to avoid the strain-induced phenomena. So now the minimum bending radius is as small as 50 micron. So quite recently, one of my students has successfully formed the high mobility transistors on 1 micron thick plastic film, and then he can nicely wrap around the even human hair, which has 100 micron diameter, without causing any significant electronic degradation. So in that way, we could ultimately improving the mechanical durability. And also for circuit level, here we measured the electronic performance of organic ring oscillators with wrapping around the 300 micron central bar without causing any electronic performance. But if I use the CMOS ring oscillator layout, the stage delay was as large as approximately 5 milliseconds, which means 20 hertz. So that is too slow. So in order to further improve the electronic performance, so we adapted two straightforward approach. So one is to use the high mobility organic semiconductor, which is C10DNTT. So that's easily achieve the mobility of 4 square centimeters per second quite reproducibly. Another approach that I adopted is to use the novel pseudo-CMOS layout. So of course, the CMOS required both P-type and N-type semiconductors. However, N-type semiconductors have still air stability problem that degrade quite rapidly in air. And also, mobility of N-type semiconductor is usually much less than P-type semiconductors. So that's ultimately limit the electronic performance of CMOS. So to remove the bad aspect of N-type semiconductors, so here we use the pseudo-CMOS circuit, so which comprises the 4 P-type semiconductors, and we can make the so with combining the pseudo-CMOS and high mobility organic semiconductors, so now we achieve the world's fastest organic TFTs with an operation voltage of 1 volt, and now the oscillation frequency becomes as large as 4 kilohertz. And if you so this is the literature value. So now we could significantly reduce the oscillation frequency by 2 orders of magnitude lower than the conventional CMOS layout. So another important progress in our group was the combination of super inkjet, atolita inkjet, and organic transistors. So in order to further improve the frequency response, the miniaturization of organic transistor is important. So now we directly print the 1 micron channel by using atolita inkjet. So in this way, we can achieve the world's largest transconductance of 760 micro Siemens per millimeter from which we evaluate the cutoff frequency as large as 7 megahertz. Of course, this is just a numerical analysis, but so in order to achieve real 7 megahertz, we have to remove the parasitic capacitance. But in any cases, this device exhibits the really great potential of printed transistor that should work even in the megahertz regime. So this is the quite brief overview of our recent progress of printed organic transistors. And then we try to apply this technology to make the robotics E-skin, which is largely a flexible sensor matrix exactly. So first, our effort was made to make the flexible devices to be stretchable. So our first layout is quite straightforward. So after fabrication of flexible TFTs, we remove the unnecessary region here, like this. And at the intersection layer, here is the one sensor cell comprising one organic transistor and one pressure sensor. By using novel net-shaped structures, now we have made the stretchable robotic skin, which can be stretched by 30% without causing any mechanical degradation. Now we stretch our E-skins and apply onto a surface of an egg. So if I apply a pressure somewhere here, and then we can obtain the pressure distribution in this device geometry. So stretchability of 30% is not so bad. However, real practical application is extremely demanding. So we want to improve the stretchability more. So in order to improve the stretchability, so here is the another new development, that is printable elastic conductors. So we try to make the rubber conductive. Of course, the rubber is inherently insulating material. We have to add some dopant. So here we choose the single-walled carbon nanotube as conducting dopant. However, here is a problem. So as many of you know, the carbon nanotube tend to be a thick bundle that cannot be well mixed in rubber matrix. So to avoid that problem, so we first mix the carbon nanotube with ionic liquid to form the nanotube gel, Bucky gel. So Bucky gel can be well mixed in some sort of fluorinated copolymer. So in this way, we can make the quite high conductivity, or rather world highest conductivity among the soft material. So now we combined the printed organic transistor and the printable elastic conductors to build the integral circuit on rubber substrate. So for the specific samples, so we can stretch the integral circuit by 70% into biaxial directions without causing any significant degradation. So we are hoping the robot with sensitive skins will feel and even respond to a person's warmth while shaking hands, and consequently letting people feel that robots are warmer. So until then, so we try to make the animal skin-like imitation. But for robotics application, why not adding the more electronic functionalities? So I'd like to, so here is some experiment or research, try to go beyond the animal skin. So one of the good example is ultrasonic sensor, which works as the 360-degree proximity sensors worked in free space. So actually, we tried to make this device when I first developed the E-skin in 2003. But at that time, So electronic performance of organic transistor has extremely low frequency response that cannot be applied to ultrasonic sensors. But as I mentioned, with reducing the channel length down to 1 micron, so we could achieve the really high frequency response of organic transistor, and then we can achieve the application of ultrasonic sensors by using high-speed organic TFTs. So this is one of the good example how things are going. I mean, with improving the electronic performance of organic transistors, and then more application becomes possible. And then we expand our research activities from large area sensors to be large area actuators. So sheet type Braille displays is one of the good example of large area actuators. So the formation of Braille dot can be electrically written or erased by using organic transistor memory matrix. So as you can see, the sheet type actuators based on Nafion can pop up the surface like that, or the formation of Braille dot were erased electrically. So now we are thinking the robotic skin, the application of robotic skin is not limited to the robot, humanoid robot. So that can be applied the variety of objects. So now we reach the kind of conclusion. So it is quite conceptual, but the people live in the real space, and the computer is calculating the cyberspace. It is not trivial to connect the real space where people live and also cyberspace where computer is calculating. So I thought the E-skin is one of the ideal devices which try to make a bridge between real space and cyberspace. So for example, if there is no E-skins on the surface of robot body, so robot brain does not really recognize where is the surface. So in that way, robot skin can help to make a really good bridge between cyberspace and real space. So that means robotic skin can connect the two worlds, and that is quite helpful to realize the new application. So, and then at the last maybe 10 minutes, I'd like to describe some of our new research efforts in Tokyo. So now we are considering, so what is the next breakthrough for the artificial skin? So I believe that will be biocompatibility. So of course, the softness of organic material is suitable for the bio application, but current robotic skin does not have any biocompatibility. So then our application is quite limited. So, but if we make the flexible devices to be biocompatible, so we can definitely consider the implantable devices or other biomedical application. So why we want to go inside the body? So as many of you know, because versatile bioinformation can be considered. Of course, squid MRI or ultrasonic can detect the versatile bioinformation from outside, but going into inside, we can definitely improve the spatial resolution, improving the sensitivity, and also abundant chemical information can be obtained. So worldwide, the competition started toward bio and medical application. However, all of those research are still quite early stage, and many of the research groups are still working on just discrete devices or only passive component. So only the research group at the University of Illinois conducted by Professor John Rogers' group has already developed the fairly large-scale integration, and which was put onto a cat's brain to detect the signal from neuron. So here I would like to introduce some of our latest progress in our group. So in order to introduce the flexible devices into body, so we definitely sterilize the flexible devices. So here I would like to report the world's first sterilizable flexible organic transistors. So we developed the flexible organic transistor which can be sterilized in standard sterilization process that required the heating process at 150 degrees Celsius without causing any degradation. The experiment was quite straightforward. So I just distribute the bacteria on the surface of organic transistor and then annealed at 150 degrees Celsius for 20 seconds. Now all the bacteria were killed, but important thing is that the electronic performance of organic transistor didn't change at all. So in this way we could succeed in sterilizing the organic transistors. So however, here I also achieved the operation voltage of 2 by using self-assembled monolayer. But perhaps you may concern about the thermal stability of self-assembled monolayer because it is only 2 nanometer in thickness. So the big question was whether such a thin film can be stable at the temperature exceeding 150 degrees Celsius. But we found by detailed the structural analysis by using NEFSAFs, the self-assembled monolayer is extremely thermally stable even after we anneal 160 degrees Celsius. So indeed, we measured the tilted angle of self-assembled monolayer as a function of annealing temperature by using NEFSAFs. So this experiment was done in collaboration with Professor Lin-Lu, Princeton University. So with elevating the temperature, the tilted angle could be slightly increased, but there is no drastic degradation. So in this way, we could confirm how thermally stable such a thin self-assembled monolayer is at high temperature. So here is the another development, that is organic amplifier. So the biosignal is so small, something like 10 microvolt to 100 microvolt. So we definitely need the good amplifier. That means analog circuit. So, but at this moment, almost all the researchers in the field of organic electronics work on the active matrix. That means digital circuit. So we try to make the two-dimensional array of amplifier by using organic thin film transistor. So here is the kind of new development. So as I mentioned, we always use recently the pseudo CMOS comprising 4 p-type semiconductors. However, here I replace the regular organic transistors with floating gate structure. As perhaps you know, the floating gate is a kind of memory device used to make the flash memory. But we didn't use the floating gate to make the memory matrix, but we tried to remove the performance distribution of organic transistor, which used to be a very problematic to make the analog circuit. Indeed, when we make the 8 by 8 amplifier, so there are fairly large performance distribution. But after programming or accumulating charge at the floating gate structure, so we can remove the performance distribution, something like that. And also, we characterize the frequency response of organic amplifier, and then found the gain exceeds the 100, even at the frequency of 100 Hz. So biosignal is very small, but it's quite slow. The important frequency range is somewhere between 1 Hz to 100 or 100 Hz. So now we have already achieved the, we have already covered important frequency range, yet the gain exceeds the 100, which is very important to detect the small biosignal. And also, we are now trying to use the bunch of different substrates, like shape memory polymer or biodegradable film. So here I want to report the fabrication of high-performance circuit on unconventional substrate, like shape memory polymer. So after surface planarization, we make the organic transistor active matrix on shape memory polymer that will be wrapped around the cylindrical bar in this kind of helical geometry, and then apply the 150 degrees Celsius, remove the central bar, and then we keep this kind of structure. So we use this technique to electrically functionalize the surface of medical catheter, and then try to detect the pressure distribution. So now we are trying to apply the flexible devices for biomedical application with adding the sterilization capability and also biocompatibility, and improving the frequency response, and also the gain of amplifier to detect the tiny signal. So before concluding my talk, I'd like to acknowledge my collaborators. So this is my group picture, and who make the many of our flexible prototype. And self-assembled monolayer was explored in collaboration with Max Planck Institute, and structural characterization of self-assembled monolayer was done in collaboration with Lin-Lu at Princeton University. So today, there is no strong conclusion, because there is, well, still all the work is ongoing. But I'd like to say two things. So, well, as perhaps you noticed, so I'm trying to get closer to living things step by step. So we started from a rigid substrate and try to adapt the plastic film, and we have made the circuit on rubber. And in order to make the biocompatibility, achieve the biocompatibility, now we are playing a little bit around the gel or liquid crystal. So in that way, the future electronics is going to closer to a living thing. And the last thing is how we can sense the emotion electrically. That should be a big challenge. So biocompatibility, implantable, or we do not really know the answer. But if you try to detect the emotion electrically, I hope you bet my idea of robotics E-skins. So thank you very much for your kind attention.
Well, thank you very much, Professor Someya, for that wonderful presentation. Questions, comments?
Could you elaborate a little bit how you did the programmation with these floating gates, how you get all the transistors to...
Yes. So, so here is the circuit diagram. Each cell has the floating gate here. That means we have to characterize all the amplifier cell. So, and then after measuring the performance distribution, so we decided how much carriers should be accumulated at the floating gate, and then try to accumulate the exact amount to each floating gate. So in this way, we can change the threshold voltage with changing the amount of accumulated charge. Try to remove the performance distribution. So we have to measure all the sensor cells, but we can remove the performance distribution electrically after fabrication.
And how stable is the programmation?
That's actually quite a good question. And well, retention time of a floating gate memory is the order of day. So that means we have to refresh our memory cell maybe in a day, but that shouldn't be a problem for the specific application.
Regarding that slide, 2 micron, I think it was silver, right? And you mentioned that we apply electric voltage. Can you also a little elaborate on that one? So you apply voltage to the ink and the surface, or it's something else?
I'm sorry?
Is it like inkjet printing and electrospraying, or it's something else? To get such a narrow
voltage between the jet and the surface.
Well, we use the a kind of fine glass pipette, and then apply the electric field between tip of nozzle and substrate, and to get the really fine droplet from an inkjet nozzle.
So the voltage is applied to the ink or the tip?
Well, we insert some of the wires inside the ink.
Ink.
Yeah.
So it is electrospray and inkjet.
So yes.
In terms of the implantable devices that you are working on, I mean, what are the kinds of first applications you are looking at there with those devices?
Well, we started the discussion with medical doctor. They have a bunch of different specific applications, like where they try to put the anyway, this is electronic devices, so they try to detect the biosignal from brain or heart for medical diagnostics, and they try to know the exact position of defect or something. So, but such kind of concept will be proved after a long time research. So
There is still work to be done. Okay, I don't think I see any other questions or comments. So before we thank Professor Someya, I'd like to mention that unfortunately he'll have to wake up extremely early tomorrow morning to catch a flight eventually to Tokyo, and will make his trip even more complicated by giving you this little souvenir of the of your presentation today. So let's thank you.